technology and the advantages. In this part of the webinar, I'll specifically focus on the Tedlar clear film-based backsheets and how it contributes towards lowering the total cost of ownership for asset owners. As was mentioned, I work for DuPont, and DuPont has been a big player in PV for 30 plus years. The three flagship products that have been serving the PV industry are a silver metallization paste, DuPont Solamet, the Tedlar-based backsheets, one of the examples of which we will be talking today, and a silicone encapsulant, the Photosun, that you see on the right over here. And, we always try to balance performance with long field reliability, which together would deliver long years of proven performance in order, in turn, try to drive to lower LCOE. So if we think of LCOE, there's the cost part, as is shown over here. There's the module cost, the operations maintenance cost, the installation cost, the balance of system cost, and then on the other side there's the performance related stuff. The durability of the modules, the energy yield, the system performance, and obviously the module efficiency. Now the way we try to do it is we try to recast this thing in a slightly different mode where we capture all the different aspects. And then we try to reason out how we could add to the whole equation in order to lower the total cost of ownership. As you see here on the left, I'll take you through these four buckets that we have recast all these elements in an LCOE in terms of proven material reliability, in terms of performance, yielding higher energy, in terms of cost, through lowering the cost of installation, balance of systems, and operations and maintenance. And then something that Ivan also referred to, a more mature manufacturing process involving less capital investment. So taking up the first bucket over here, what do we see in terms of material reliability? One of the things that the DuPont Tedlar product is proud about is its 35 plus years of field proven record. Obviously not in bifacials because bifacials were not there, but the technology of the backsheet and the material is very much similar. I'll come to the different aspects of how material reliability plays into the whole thing. So the first question that you might ask is why do we need long-term field-proven record? Although the answer is probably pretty obvious, we always try to point towards field performance as our first metric. What I'm showing here in this chart over here on the right is data from a field program that, like some other institutes, DuPont also drives. And this is a program that we have been running for over 10 years now. What is seen over here is that year over year, there has been an increase in the number of module defects over the years. And if we now narrow down to our this part of the discussion of the webinar, we are also seeing a corresponding increase in the backsheet defects, be it polymeric backsheets or glass backsheets, which do not go back much further. Now, this report is actually based on a lot of data globally collected. As you see here, over 3 gigawatts of total power. So this kind of points us to the fact that all modules are not really created equal. So attention to the bill of materials is very critical, as Ivan pointed out, the rigorous process that Vikram Solar runs through in order to ensure long-term reliability and therefore long-term return on investment of asset owners. Okay, so armed with that information, what do we know about any record of the clear Tedlar-based transparent backsheet in the field? Obviously, as I pointed out, there was not much of bifacial out in the field, and therefore there is not a lot of data. However, I want to point out to this one of these examples from the field. There are several of these where there are some building integrated photovoltaics, and this particular one is in Netherlands, in Amsterdam. And this has been in the field. At the time of its inspection, it was 18 years. Now it's 20 years. And essentially no degradation in the backsheet. No yellowing, delamination, cracking, anything. Gives us a lot of confidence in the field proven record of the material. So this was the older generation of the transparent backsheet. In 2019, DuPont then launched the new transparent backsheet made on based on the improvements in the clear Tedlar film, which actually won the 2019 PV Magazine Award for one of the best innovations. And as we are seeing here on this cartoon on the right, the innovation in this case in the air side or the outer layer, which is the Tedlar layer, and that in turn protects the core and the inner layer of the backsheet from things like UV, things like abrasion, and obviously also holds up to other stressors in the field. So let's take a look at the properties of this transparent Tedlar film. Obviously, what's required of it? You heard about transparency and how we need transparency across the wavelength ranges. So on the right, I'm showing here how this transparent Tedlar film has a very flat 92 to 94% optical transmission over an entire range of solar wavelengths. It needs to have robust mechanical properties and obviously UV protection for the underlying layers. We'll come to some of these. Just to start out with, these are some of the starting out numbers, and I'll detail on why these are important and what these mean in the next few slides. Once we have the Tedlar film, now obviously the backsheet is, as I pointed out, is made out of this Tedlar film on the outer side, and then a transparent PET core and an inner layer. This is also a fluorinated coated layer. On the right, we are showing how this transparency, the optical properties, holds up after 400 kilowatt hours of UV exposure from a xenon source, which actually simulates the sunlight the best way. So what we see here is the optical transmittance, which was at about 94% is very straight, flat on all across these hours. The other interesting thing is, as polymers are exposed to UV, the yellowness in the polymers can go up. In this case, it does go up a little bit. However, compared to any degradation in field performance, this is a very low increase, and it absolutely does not affect the performance in this case. Now, what does it do in the field? Here's an example from a tier 1 module maker. They actually put out bifacial modules with dual glass and bifacial modules with the glass transparent backsheet in the field. And for 30 kilowatt hours of UV exposure, what we see here is the dual glass modules actually incurring more power loss, as you see here, 2.7% versus the 1.33. Why this is the case? If we look at the transmittance of the UV in the UV of the clear backsheet versus 2mm glass, we see here that beyond 350 nanometers, so shorter than 350 nanometers is the place where there's a lot of harmful UV that's present in the solar spectrum. And bifacial and the clear transparent backsheet actually has a much lower transmission, and this in turn compared to glass, and this in turn can protect the rear side of the module from UV degradation, as well as a degradation of the POE encapsulant that's there on the rear side. So here's an example from the field of actually how this improved protection from UV versus glass can deliver in the field. Next, we are looking at two other very important properties. The first is obviously mechanical properties, right? So you need these polymeric backsheets to hold up their integrity, to be robust mechanically over the course or lifetime of the module. So on top, what we are showing here is, and this mechanical property is measured by the retention of the elongation. So because these are polymeric materials, they can stretch, and they can, if they become brittle, they can crack. However, if the elongation is retained, we are confident that this will hold up in the field. What we are seeing here is on the top plot over here. I'm showing elongation after UV exposure for again 400 kilowatt hour, which is which actually corresponds to 30 years of field exposure from the backside. And as you see here, both in the two directions of the module, the MD direction, which is the machine direction of the module, and the TD direction, which is the transverse or the perpendicular direction, the elongation is pretty flat. Similarly, after damp heat of 3,000 hours, there's almost no loss of mechanical properties, in this case, the elongation, as we see here. By the way, the requirements for IEC or some other accelerated tests like the PVEL or DNVGL test is much lower than this 150% or way over 150% that we are getting here. We also look at abrasion losses, and this was mentioned by Ivan. The way we measure it is through an ASTM standard test, which actually is much harsher than any field condition that the modules would see. This is essentially 100 liters of sand and surface heating. So what we see here is the Tesla-based transparent batch sheet on the left. We are measuring the light transmittance, and it only loses a fraction of a percent light after the entire test, which is way over the lifetime of the module. And compared to some other competitive materials, you can clearly see the difference over here, both in terms of the loss in light transmittance, and on the right here, an equivalent test which shows how much of sand is needed to actually wear out the backsheet, which is significantly more than any other competitive backsheets, and also significantly more than anything that a backsheet would see in actual field deployment. Next, I'd like to show some results on PID, as was also mentioned by Ivan. Bifacial PERC cells, depending on the passivation, the rear side passivation, if it's not optimized properly, can lead to losses in power. Showing here results from full-size commercial solar modules comparing glass and a transparent backsheet. More importantly, I would like to draw your attention to the rear side results, and we see clear differentiation all the way up to 384 hours. Mind you, this is again much more harsh than is required by, again, any IEC or other accelerated tests. So at the 192-hour level, there's a clear difference between glass backsheet and glass in terms of power lost. This again has been repeated by another tier 1 module maker, and in that case, actually, the clear backsheet modules almost lost no power after 192 hours. Okay, so Ivan did mention that all Vikram solar modules go through the PVEL or DNVGL testing, which we also put a lot of emphasis on. So in this particular PVEL sequence or DNVGL sequence, they have now introduced a backsheet durability sequence as part of the PQP program. And this clear backsheet has been taken through it, the full sequence, and it's shown here on the left over here, and without any cracking, yellowing, or delamination. So essentially no defects. However, as it's pointed out in the block over here on the right, there are several cases of faulty backsheets that have gone through the test and have ended up showing defects, very much like defects that are seen in the field. So that brings us to the next bucket, the energy yield bucket. I'm showing here some results, again, field results. We always try to go back to the field to prove our point from a tier 1 module maker. What you see here are 4 different installations of sand fixed installation, sand tracker, and a different surface, a cement with a fixed one, and a cement with a different type of cells. But in all these different tests, over a period of 6 to 8 months, this was done with multiple modules in actually an array. We see that the bifacial modules with Tesla transparent backsheets actually outperforms. This is the amount of energy gain that you get over glass modules in all these installations. The reason that was kind of alluded by Ivan, we believe, is that the bifacial modules have Tedlar on the back, and Tedlar actually has much better infrared transmission spectrum at wavelengths longer than 3 micron compared to glass, and this helps them to handle the heat dissipation from the PV modules better than the glass backsheet. So this work, we are actually right now trying to delve deeper into it to figure this out further. Hopefully I'll be coming back and showing you more results on this, but this is the main belief right now. Coming to the next bucket, towards lowering the cost of installation, balance of systems, and operations and maintenance. Again, something that was mentioned by Ivan. I'd like to add to it by saying that there's a general trend in the market of going towards larger size modules. So 400 and 450, 460 watt modules are very common now. And there's a push with different module makers to go to 500 watt modules. With that, the module size and module weights would increase even further. And the difference in the weights of glass transparent backsheets and double glass modules would still contribute to the glass transparent backsheet modules to be very attractive. Again, they are less prone to damage during transportation and handling. There's no extra cost during installation versus simpler monofacial modules, and also that these being lower weight. So we believe that these are better fit for a higher power and definitely for as the market moves towards bigger size modules. Ivan also mentioned the lower O&M cost. I'm showing some actual results here. This is actually, again, a standard China standard test for soiling resistance. What we see here is a comparison between a transparent Tedlar backsheet module on the left and glass on the other. And before rinse, we see all the soiling over here on the top. And after a rinse, which is part of the standard test, you can clearly see the difference between the transparent backsheet versus solar glass, which is used here. On this chart, again, if water is not used and any of the simple organic solvents are used to clean the modules, by the transparent Tedlar, which is shown on the right over here, clearly outperforms any of the other clear backsheet modules or materials in this case, either an FEP or a PET transparent coated. Brings me to my last bucket over here, and just very quickly, as I had mentioned, and again, Ivan being a premier module representing Bikram Solar, who are a premier module maker, can speak more to this. But we all know that, as we mentioned, bifacial, in this case, clear transparent backsheet module making involves less capital investment versus the glass production line. No loss in yield rate. This was again hinted at by Ivan. With the POE encapsulant, there's stricter process control that's needed, which can actually result in yield losses. With bifacial modules enabled by transparent backsheets, we believe that EVA can be used at the back because of the lower PID loss, and therefore we can take down this yield loss. And again, faster production speeds would lead to higher capacity. The other thing that I did not point out in detail in my presentation is there's a move towards glass modules coming with thinner and semi-tempered glass, which actually increases the risk of glass breakage during the module lamination and further handling. This again can slow down the production speeds and also can lead to field issues and defects in the field. So when I bring all of this together, we now have filled all these 4 buckets, all the way from material reliability on a long term, higher energy yield with actual field data that's going on now, lower installation and other costs involved, combined with the mature manufacturing. We see a clear path towards lowering the total cost of ownership through adopting this clear, transparent Tedlar-based backsheet technology. With that, I thank you for attending the webinar and listening, and I'll be open to any questions